Good evening. Made it through the day, another day. Attacked from the sky twice. Boom, boom. Serious stuff going on out there. The speed of light. The way I've been explaining it, the best way for me, I think, to explain it to you guys, the way I see it, is the diameter thing, right? People used to say to me, what difference does the diameter of a light source make? All of the difference, not the speed, but the distance that the light is radiated. You're being told that light travels at 299,000, I haven't even got it up here, 299,792 kilometers per second, right? Right, you're being told that light travels at 299,792 kilometers per second. Sounds great until you get to the size of the sun. With a diameter of 1,390,000 kilometers, if we divide that number by the speed of light, we get the number 4.6. That's 4.6 seconds for the sun to radiate its light the distance of its diameter. 4.6 seconds. Now, it's really, really silly, all right? Now, what I'm saying, light is absolute. There is no finite anything. If a light source turns on, boom. And we're talking about the diameters to focus on here, not the speed of light, the distance per second, or how many diameters per second, which is, with the sun, 4.6 seconds to radiate its own light, the distance of its own diameter, 299,792. Fits in this sun 4.6 times, 299,792, 299,000, and so on. It takes 4.6 seconds for the sun to radiate its own light, the distance of its own diameter. I assure you it doesn't. It just doesn't, right? This light source, we're not talking about its light touching something. You could put your hand over it and it make a shadow after 30, 40, 50 meters. No chance. We're talking about our eyesight detecting it. I've settled on the 5 kilometers, right? It's a very, very, very modest estimation. It's probably 7, 8 Ks, right? When I turn this on with my hand up here, somebody who's 5 kilometers away, if I'm looking at this bulb and I turn it on like this, the guy 5 Ks away, facing this light, will see it at the same time as me. There is going to be no delay. Yeah, but we're talking a bulb. When it's the sun, it's the distance. Yes, the distance is 150 million kilometers. But the diameter of the light source, it's 1,390,000 kilometers. It's only 108 diameters of itself away from us. This is the thing. This is the bit. Yeah, but it's the sun. The speed of light dictates absolute bollocks. It's a lie. It's obvious, even from the methods that have been said to have measured it. The Roma thing. Look, let's not go back there. What I wanted to do tonight is we're going to use the moon as the sun, right? Keeping things to scale. One of the biggest things about all of this is the 108 sun diameters that are in between the sun and planet Earth, right? It's important because it's only 108 sun diameters. This 5 centimetre bulb, if it's only 108 of its diameters away, that's going to be what? 5 centimetres, that's 550, 5 metres and 40, wasn't it? Yeah. 5.4 metres away from us. That's nothing, is it? 5.4 metres away from us. That is how far away Earth would be if the sun were a 5mm bulb. It's not far away at all. Why would anybody think that it would take 8 minutes and 20 seconds for this to radiate its light 5.4 metres? Ridiculous. But when we get to the size of the sun, 1,390,000 kilometres, it takes 8 minutes and 20 seconds to radiate its light 108 diameters of itself. This has got jack to do with the actual speed of light. This is about common sense and understanding that a light source, there isn't a light source, there isn't anything that radiates its light that slowly. Apart from UY Scuti, because the bigger a star gets, the longer it takes to radiate its own light the distance of its own diameter. 2 hours and 12 minutes. It's got a diameter of 2.377 billion kilometres. So they say, right? We divide that number by the speed of light, we get 7,928 seconds, I think it was. Divide by 60, you get minutes, you keep going. 2 hours and 12 minutes. So this light bulb, watch, bang, quick, it can be seen at 5 kilometres away, 100,000 diameters in the flick of a switch. When we get to the sun size, switch it on, it would take it 4.6 seconds to radiate its light, just one diameter. But this is doing 100,000 diameters in a switch flick. Then we get to UY Scuti with a diameter of 2.377 billion kilometers. It takes UY Scuti 2 hours and 12 minutes to radiate its light the distance of its diameter. It's ridiculous. It really is. You put this, look, let's not go there. Right, now, I said I was going to do the moon. Let's do the moon. So here we are. The moon. Boom! Up in our sky. We're going to make it the sun. Right? The distance to us, etc. The moon has a diameter of, so they tell us, 3,476 kilometres, right? First of all, we're going to multiply that by 108 moons, because that's how many there are in between Earth and the sun, right? So we're going to call it moons, but it's really the sun. We get 375,408 kilometres. So, if, keeping things perfectly to scale, if the moon were our sun, planet Earth would be 375,408 kilometres away from it. The not freaky, the thing is with this one, is the moon is already 380,000 kilometres. That's the average distance that it is from us. So basically, look, for 5,000 Ks, we don't even have to mess with anything. We just leave it as it is. That distance, if the moon were our sun, the distance that the moon is at is nearly bang on the money. And the other thing is, during the solar eclipse, the sun is behind the moon, and it has the same diameter roughly, doesn't it? So we know that that's right, okay? So the sun that's behind the moon during a solar eclipse, drop kick, it's not playing this one, it's out of the picture. The moon has become the sun. Daisy the cow, loving it. Ah, the size of that moon, can I? Go on, jump on. And somewhere else. Oh, is that the only one? Yeah. Oh no, there. Daisy the cow. What we have is the perfect scenario. We picture the moon as our sun. Earth. What happens to Earth? The only difference in all of this is Earth. We have to modify Earth. 109. The moon has a diameter of 3,476 kilometres. We want to find out what diameter Earth would be. We divide it by 109 because there are 109 Earth diameters in the sun. So we divide sun's diameter by 109. We get 31.8 kilometres. I've made it 32. What we have here, this is perfectly to scale, right? This is perfectly to scale. If the sun were the moon, if the moon were the sun, with that diameter, the distance to Earth would be 375,408 k's. It's already 380,000 k's, that's the average distance. So it's smack on the money, right? And Earth would have a diameter of 32 kilometres. Earth is only ever a reference point. It doesn't change the speed of anything or the distance of anything. Earth is just a reference point, because otherwise it doesn't really mean that much. But when we see Earth and we know how big it is, you can make a better picture, mental picture of what is going on. 32 kilometres in diameter. Would we know the difference? No. If we woke up tomorrow and our whole universe had shrunk, everything had shrunk proportionally together down to the size of a 45 micrometer Earth at a distance of 54 centimetres from a 5 millimetre sun, we wouldn't know the difference. We would not know the difference. This is perfectly to scale, right? Get in there. Come on, not now. Calm down. It's the budget. NASA takes it all. NASA's taking the real science people, the real science budget, launching it into imaginary space. All that money. Now, look at this. Look. Let's turn all this off. Don't forget, this is perfectly to scale. This is the thing people aren't understanding. This is perfectly to scale, right? The sun, if it were a 5 millimetre light bulb, keeping everything in the perfect proportion, the perfect to scale, right? The same ratio, the distance from this bulb to Earth would be 54 centimetres. And Earth would have a diameter of 45 micrometres. There are 1,000 micrometres in a millimetre. Earth is 45 of that 1,000. So what? 22nd of a millimetre or something, right? How long does it take for this? Look. You could just, it might as well be off, right? Turn it on, and look at the distance that it goes. I know what people are saying, but it's only a freaking thing on a blackboard. That's not the real distance between the sun and Earth, for crying out loud. But we're talking about diameters. And this is exactly the same as a sun with a diameter of 1,390,000 kilometres being 108 sun diameters away from Earth because of the diameter. 1,390,000 freaking kilometres. This is the bit that people are missing. This is to scale with the real thing. Earth would be the tiniest speck of dust, the tiniest speck on that red line. And all of this right here, that's perfectly to scale with the real thing. Now, the diameter of this bulb, yes, it is only on a blackboard, and there is only 54 centimetres in between the imaginary Earth and the bulb sun. But these things are perfectly to scale. Every time we increase this distance, if we double it, we have to double the diameter of the bulb. It grows with it. So it's always going to be getting bigger and bigger and bigger as the distance increases, right? There is never going to come a time that this bulb is going to be intimidated by the distance that it has to radiate its light to Earth, because it's always going to be this scale. It's always only ever going to be 108 of whatever diameters that sun is along the way, all the way up to the real sun. So it's about common sense, knowing that this is perfectly to scale. Why is it that people have accepted that when it gets to the sun size, instead of it just behaving according to its diameter, boom, it's going to radiate its light, what was it, 139 billion kilometres or something, works it out as, and that is that is on the low side. And that was because the light bulb, I said 5 kilometres, right? I said 5 Ks. So light bulb, 5 kilometres, right? To be seen. Somebody can see it. And this has a diameter of 5 centimetres. We times that by 100,000 and we get 5 kilometres. Right? So, the obvious thing to do is, because we're talking about diameters and the way they radiate light, 100,000. Let's stick to what we think the bulb does, right? Now this is way on the low side, right? 100,000. Alexa, what's 1,390,000 multiplied by 100,000?
1,390,000 times 100,000 is 139 billion.
139 billion kilometres. This I can start to live with, right? Now this, if the sun, and I guarantee you it does, radiates light the same way, the same manner as this light bulb, and it can crack 100,000 of its diameters, boom, like that. I put this on over the river, 5 Ks away, somebody looking in this direction, They see it when I see it. It's instant. It's either on or it's off. The sun, if it did that, that's 139 billion kilometres. So if somebody was looking towards the sun, 139 billion kilometres away, if it turned on or it turned off, people would see it with the naked eye. Absolute light. Just like I say, we see Proxima A and B, Alpha Centauri A and B. We see what they are doing in real time. It's absolute light. There is no delay. It is a fact. But what seems to have happened, this is the basic way to work things out. This is the foundations of math and subtraction, addition, freaking multiplication and stuff, isn't it? This right here explains everything. But everybody's talking about hypothetical particles doing this and that, and photons lasting forever. There can be no light without a light source. Earlier on I was shooting bats with a laser, and as I was doing it I was thinking about that. You can see the laser, but well, I know it's only however far it's reaching up. But when I hit the button, you don't see a zzz, do you? It just goes bang, bang. It's so fast, right? That's absolute light. You won't see the beginning and the end in all, like you won't see it go like that, never. It's too fast. All you see is light, bang, from the beginning and as far as it's going to reach. You see it all together. You wouldn't know if it's gone that way or that way. That's absolute light. You cannot tell the difference. Where is that? Let's see if I can get what did I do with them? Right, lasers. God, I'm having a shocking time with my equipment. How far can they be? Oh God, alright. Where's my other one? I always find it better with the green laser. Alright, you go. See, can you see this? See, you can't see it. You wouldn't know it's there, would you? You wouldn't know that this green light is anywhere in between us, would you? Right, move out of the way. Unless there's dust or something. If a light source switches on like that has over there, and it's obviously facing that way, it does not matter how far it is going to go. But however far it is going to go, it will reach, bang, at absolute speed. Somebody looking at the laser, right? It doesn't matter if I was 50 kilometres away, 2,000 kilometres away, 4 kilometres away. However far that laser is going to reach, it would reach me, my eyesight, bang! Even if I was 150 million kilometres away. If the laser had the power to reach that far, it would do so, bang, at absolute speed. And that is exactly what the sun does. 4.6 seconds, folks. 1, 2, 3, go. You have to see this for what it is. You have to see this for what it is. So we have the moon, we're looking up at the sky, and the moon is our sun. It's the usual distance it is away from us. Nothing has changed. The only thing that has changed is us. Us. We've shrunk down to 32 kilometres, the diameter of Earth. That's what I was going to say. We would not know if we woke up tomorrow morning and our whole everything, universe had shrunken down, that we were on a planet that measured 45 micrometers. Our sun was 54 centimetres away from us, and it was a 5mm light bulb. We came out tomorrow, woke up, got out of bed, and that had happened, we wouldn't know. We wouldn't know, because if everything shrunk down at the same, perfectly in proportion to everything, why would we know any different? If we weighed ourselves, everything would have reduced in size. That means the scales would have reduced in size. Everything would have reduced in size. We wouldn't be weighing, let's say I weighed 85 kilos. I wouldn't be weighing 85 kilos, but the scales, where they usually went up to 85 kilos, when I got on those scales, if we shrunk down to that size freaking solar system, and I got on scales that had shrunk down with everything else, they would still go to 85 kilograms. If I looked at the thing, none of us would know the difference. If everything reduced, we'd be none the wiser. But this star would be radiating to us as soon as I hit the switch. Can you see what I'm saying? It stays in the correct ratio. The proportion, it's proportionally correct, is what I'm saying. The same as a 1,390,000 kilometre sun, 150 million kilometres away from an Earth with a diameter of 12,742 kilometres. This bulb to that 45 micrometer Earth is exactly that picture, just smaller. Everything is in proportion. The bulb, boom! The sun is going to do the same when it's 1,390,000 kilometres in diameter. It's not going to radiate, it suddenly start going, bleh. 8 minutes and 20 seconds to cover 108 of its diameters. It's this bit right here. The freaking speed of light. This is science versus science. This is a logic versus common sense versus rational thought versus ridiculousness, isn't it? It is not logical to think anything radiates its light that slowly. It just isn't. And for those people that keep screaming, prove it. No, you prove this ridiculousness. Well, don't say standing on the shoulders of giants that so many people have already discovered and done this study and that study, and it's been retested God knows how many times, because it hasn't. I guarantee you it hasn't. It's impossible. The light radiating from the sun is absolute, and we know that because of the solar eclipse. There is zero delay in between the moon were here and the sun's light, bang, reaching moon, casting the shadow onto Earth. There is no delay because the sun is directly behind the moon. If it were finite Mickey Mouse, finite light, firing off Mickey Mouse photons, it takes 8 minutes and 20 seconds, and in that time, when they leave the sun, planet Earth spins 2.08 degrees on its axis anti-clockwise. So a sweet spot on planet Earth cannot be lined up with the shadow and the sun, because there is an 8 minute and 20 second gap in between two. It just cannot happen. I don't know how people keep finding reasons for it. Let's listen to a little bit of ridiculousness. Just the build-up. It's only a couple of minutes, right?
One of the most enduring ideas in all the universe is that everything that exists now will someday come to an end. The stars, galaxies, and even the black holes that occupy the space in our universe will all someday burn out, fade away, and otherwise decay, leaving what we call a heat death. But perhaps there are exceptions to this general rule, and some things will truly live on forever. One such thing is the photon. All of the electromagnetic radiation that exists in the universe is made up of photons, and photons, as far as we can tell, have an infinite lifetime. Does that mean that light will truly live forever? It's not necessarily an easy question to answer. We can fathom circumstances where they might decay, convert into other particles, or undergo unexpected changes. In the 1910s, Vesto Slipher was working at the Lowell Observatory in Flagstaff, Arizona. During this time, he focused on observing what were then called spiral nebulae, which we now know as galaxies. Slipher used spectroscopy to study the light from these distant objects. This technique allowed him to analyze the spectrum of light emitted by these nebulae. In 1912, Slipher discovered that most of the spiral nebulae he observed were moving away from Earth at high speeds. This was evident from the redshift in their spectra, indicating that the light waves were stretched as the objects moved away. As the fundamental particle of light in all forms of electromagnetic radiation, photons play a major role in the universe.
Listen. It's all a lie. It's the whole relativity thing. It is a mindfuck. 100% slam dunk. There is no evidence for the speed of light ever having been measured. Not from the sun and the stars, right? And you think it's all the same, right? Olaus Roma in 1676, right? It is said that by observing Jupiter and Io, he detected a light delay, right? From when we were closest to Jupiter to when we were the other side of the sun. So Jupiter's here and we're here. So we're closest to it. And as we went around the sun in our orbit, when we got to, well, say here, because you would have had to see Jupiter around the sun, we have travelled 150 million kilometres and another 150 million kilometres, because it's 150 million kilometres to the sun on that side, and when we're on the other side, it's another 150. So that's 300 million kilometres difference. That 300 million kilometres, it is said to have been the reason that there was a light delay, the distance. Light being finite, it takes, what was it, something like, Alexa, what's 300 million divided by 299,792?
300 million divided by 299,792 is approximately 1,000.6938.
Oh, what did you say, 1,000? Alexa, sorry, I missed that. What's 300 million divided by 299,792?
I'm not quite sure how to help you with that.
Alexa, what's 300 million divided by 299,792?
300 million divided by 299,792 is approximately 1,000.6938.
1,000.6. So basically 1,000 of something. So now we're looking at kilometres per second. Alexa, what's 1,000 divided by 60?
1,000 divided by 60 is approximately 16.6667.
16 minutes. It would take light travelling at 299,792 kilometres per second, 16 minutes to travel from us on this side of the sun to that side of the sun. So that is the delay that he was saying he was seeing in between being closest to Jupiter and Io coming out, and us being at our furthest from Jupiter and then seeing Io coming out. But he was using a telescope. It's just another insult to people's intelligence. If he was using a telescope, see, these things, right, are so full of holes and easy to detect. If I'm looking at Io through a telescope and I'm looking at Io from this side of the sun, and here's Jupiter, and here's Io coming out, and this is Earth, and I'm looking at these two from that distance, there will be no difference when we, 6 months later, when we're round here, right, or here, we can still see Io and Jupiter, and then I look again. Bang, I can see Io again. Why on earth, even if there were a light delay, would he detect it with a telescope? He wouldn't, because it's a telescope. Honestly, see, to get to this stage, it's quite a long walk. But once, those of you who have managed to stay the course, you must see what I'm saying here. A light source will radiate its light at absolute speed. Bang, like this bulb. Every single light source in the universe. Bang. There's never going to come a time when something is so big or so anything that it's going to take 4.6 seconds. And that's only because of the sun's diameter. UY Scuti at 2.377 billion kilometres takes 2 hours and 12 minutes to radiate its light the distance of its diameter. If you can see the BS, we are talking mountains of it, because relativity, 1905, Einstein, Romer, Bradley, Fitzo. Guys, I'm telling you, that stuff has been fabricated. Slam dunk. All right, look. A few more people are asking different questions, more in-depth questions now. That means people are finally listening. I can just get the vibe that people are finally listening. This lie, I mean, every equation that has ever had C in it is wrong. Everything. Radio communication, space, Mars, ingenuity, the voyages, taking how many light years for, was it 20 minutes they wait for a message, or I don't know, from the voyages, or 18 hours, I don't know what it is. All of it is horseradish, because light is absolute. You either see it or you don't, and that is from the onset. If you don't see it from the onset, you ain't seeing it at all. Okay? Alright, that'll probably be it for tonight. But you just never know. Might be getting ready to be bombarded again by the bats on their way home. Alright, laters.